Hello, everyone. First of all, thanks to the organizer, thanks to Wolfram for the opportunity to present this new Paclet I'm developing. And I'm a researcher in theoretical physics at Suzhou University. And this Paclet is already in its third version, and hopefully it will keep improving. And so what is the problem, the data science problem, is analysis of research papers, especially on this well-known platform, which is ArXiv, which I would say includes most of physics, mathematics, and computer science over the last 30 years. Researchers typically share their papers before formal publication, but they turn out to be often identical to this. And this is certainly a big data problem because there are more than 2.5 million research articles on ArXiv. But since these are research papers, so it's also a very difficult kind of data, which I would like to call deep data. In fact, we researchers ourselves can typically understand well only a very minor part of these papers, because of course it's impossible to read them all. And in these quantitative disciplines, it's important to reproduce the mathematical calculations or to run the programs for a full understanding. So it's natural to wonder and investigate whether the new tools of data science, AIs of several kinds, can give scientists and interested persons as well precious insight into these deep data. And of course, everybody has its own opinion, even academics hold opinion. But what is more interesting, especially with today, which has become possible, is to prove these opinions, so to upgrade them from just chatting to quantitative and precisely argued scientific general claims. And these are some example questions for this data science problem. How to systematically discover research contents, authors, how to understand the general trends in academic research, how to classify, cluster, recommend papers, and suggest research ideas and perhaps general directions. So can computation, machine learning, large language models be the key for doing this sensibly and accurately? So, but first of all, as in any data science problem, we have to collect the data. So you may know ArXiv has its own API, but it turns out to be understandably flaky for large queries, so you cannot download the full ArXiv dataset. But these can be conveniently downloaded from a Kaggle challenge. It's updated about every week, but I also provide an update periodically in this Paclet, the full ArXiv dataset available with this function, ArXiv dataset. As you see, it's basically a matrix with dimensions 2 and 6 million almost, and 14, which are 14 keys, because every dataset element, every article appears in this main dataset with some main data, which is the ID, the authors list, the title, categories, abstract, and so on. So this is the main data available to the ArXiv API. An important parameter for all the Paclet functions is the category, which is the scientific field or topic. For example, high energy physics, quantum physics, computer vision, astrophysics, machine learning, and so on. And on ArXiv, each article appears with a list of categories, where the first is the most important, it's called primary category, and the others are called cross list. And in this Paclet, it's used a syntax with all to indicate that also the cross-list categories should be included. And similarly, we can consider super categories because it often happens that these share a prefix, for example, CS for any computer science field. And there is a function, archive dataset aggregate, which allows to create super dataset sharing the prefix. Here we see an example. Computer science includes about 670,000 papers. But what is really a big data problem is using the full article sources, which are often written in tech code, which is especially convenient because it's already a string. And then this Paclet has functions like archive text sections to extract all the sections. Similarly, we can extract the formulae, the mathematical formula. And I have to say, this scraping algorithm is still not always effective. So it's a bit a difficult problem, but in most of the time it works, and it will keep improving in later version. Another important data element are the authors, which can appear with different names and in different categories. So they are conveniently registered as Wolfram entities. This nice object can be used inside the functions, for example, to extract all the articles. Here, for example, for the famous theoretical physicist Edward Witten. But not all articles are equally important or influential. A tentative measure of at least the latter are citations, and we can scrape also them. And we can also draw nice citations graphs. And so if you, please be careful that if you try to run these functions now, you should call them as I've written with a bit different, but hopefully the new version will be consistent and will appear soon. And these citations are scraped through semantic scholar, which is, I believe, a fairly general API for all scientific fields. But other APIs can be implemented in future versions and can give other data. Now, let me explain what do I mean by insights. And so, why this can come from just counting. Indeed, until recently, it wasn't possible to do these big data computations, and still academia has to catch up. What is very basic can be already interesting, because not so often these computations are done. For example, of course, the total articles on arXiv are growing. Total articles submitted every month are growing. It's not surprising in the modern world. But what is more interesting is to inspect the different growing or plateauing or even decaying trend of article submissions in each field. We see, for example, some older field like high energy physics, which is going to a plateau, and newer fields like computer science, machine learning are growing even exponentially. And some fields like mathematical physics, I also happen to work on, is for some reason decaying in number of article submissions every month. So it's interesting to know this, and it is a very simple computation. A similar simple computation is counting title words. And here we see an example with some random category. Every category has its own most frequently used, most popular words. You may expect something, or maybe surprise or something else. What I found particularly interesting was to compute the most frequently used title words in all computer science. And I discovered that, for example, the words understanding and theory are pretty much rarely used. They are beyond the 100 position in the ranking, while learning, of course, machine learning, and using are at the first and second position. So anyone may ask why, and may also wonder how Wolfram fits this picture. Are we doing CS or perhaps CX? And similarly, of course, we can consider neighbor words or k-neighbor words. For example, the two neighbors on all ArXiv in the titles are this. You can recognize neural networks, dark matter, black holes, Monte Carlo language models, and these are indeed concepts, real concepts. And a finer computation, a bit less trivial, but still just counting, is studying the evolution over time of shares of words in article titles or abstracts. Here we see the example again of theoretical physics. You see on the left the most frequently used word in total ever. There are a bunch of obvious words like theory or even quantum, and but then there are very frequently used words like black for black holes, gauge theory, gravity, string for string theory, which show an interesting trend we might call a phase transition. It is interesting to notice that, to compute this, and to try to understand why this phase transition happens around the mid of the 2000s. Yeah, and if you are not convinced of counting just total words, you can count citations and study citation strengths over time. And but they see a similar trend, and of course they are correlated. A final computation is that of logic combinations, especially in abstracts. You can try to understand, for example, why black holes are getting more and more popular in theoretical physics, and we find out that what theorists consider black holes are actually half of the time holographic black holes. Oh, here's a funny picture, but yeah, in essence, holographic black hole are mathematical generalizations of astrophysical black holes, and yeah, can be useful for condensed matter physics. And of course, you can collect all article IDs with a certain logic combinations in titles or abstracts. And it seems to me this is a more effective and clear search tool than those already available on ArXiv or Google. Now let's come something less trivial than counting, some machine learning, even if the traditional one. So let's start with some basic classification. We can pick any list of categories we like. Here's some, for example, some categories like high energy theory, mathematical physics, number theory, sharing a theoretical character. And with a comparatively little number of titles and abstracts, just a few thousands readily available in the main dataset, we can train a simple neural network of a recurrent type with basically two inputs for titles and abstracts and going through a long short-term memory layer, a bunch of simple operations. And we can train this on just a laptop CPU for half an hour and obtain a quite satisfactory 92% accuracy. Similarly, we can train systematically classifiers on n categories, so n top categories on ArXiv. Here are the 20 most frequent categories. This time we use a GPU, but still a laptop one, and just train for 23 minutes, obtain 86% accuracy, and an interesting confusion matrix plot with a block diagonal structure, since the categories, as I said, they are organized by supercategories sharing a prefix. The confusion is indeed in the same supercategory, as one might expect. Similarly, we can classify autos, but I will talk more about that later. We can go on with the number of categories and include all ArXiv. There are almost 200 categories, but the first 80 cover about 90% of articles, 2.3 million articles on ArXiv. We can pick a small number of articles, just 5,000 for each category, and train for just 1 hour on laptop GPU. Obtain a 76, perhaps not so high accuracy, but a very impressive confusion matrix plot. I think this may be very difficult to obtain for any researcher, but for AI is easy. And more interesting is trying to train on the full articles, sources. Especially convenient are the article introductions. It started with this function, arXiv tech introduction. And these can be used especially to better classify authors, even within the same category. Here we pick top authors with a pretty large number of articles, but still below 1,000. And we, including the introduction with respect to only titles and abstracts, allows to improve the accuracy from 81 to 91%. It is interesting to think how one could train also on purely math content, and how one could use these neural networks. Of course, one can try to classify titled abstracts and other tests, not on ArXiv, where you don't know the topic. And but what I personally find more interesting is to use them as feature extractors. So what does this mean? So it means to modify the trained net by deleting the final layers, so that the output is not a label, a string of the topic, but a vector of numbers, typically in a very high dimension, in this case 33 or 32, as obtained by default with the default function. And so we can compute distance in feature space among different articles. For example, we pick 100 random articles among the 20 top categories. And we can use a function called ArXiv features categories nearest to find the k neighbors, in this case 2 neighbors, in feature space of each article. And this effectively is a basic recommendation mechanism. And by this very same general idea, we can also cluster papers by k nearest articles in feature space. And we can do that by drawing graphs like this, where I use colors to distinguish the categories that turn out, as expected, to constitute separate clusters, and also nearby cluster make very much sense. For example, you see here the cluster in the bottom is made of computer science in green. Then in the top left, you have blue and light blue, which is gravitation and astrophysics. And in the top right, you have in red and orange high energy physics. And similarly, you can classify any number of categories. Of course, the general picture depends on the sampling. There will be better functions in the new versions to choose your own articles you are interested in and cluster them. And so it's very beautiful to draw this graph in Wolfram language and explore them even in 3 dimensions. If I can run this now, yeah, you see. And this concludes the traditional machine learning part, but now finally the hot topic of these years, the large language models. So the fact is titles and abstracts are often difficult to understand even for humans. These academic papers. And but what is typically more insightful are introductions. We can extract them systematically by scraping, and they are naturally suitable also to be fed into LLMs. So it turns out that often authors in the introduction define specific concepts. So we can use the introduction to help the LLM explain a specific concept. In this case, Viterbi algorithm with a special papers, which turns out to apply it to gravitational physics, gravitational waves. And you can specify any prompt you like. These all inherits the options of LLM synthesize. But you can also avoid using the LLM at all. Since it often happens, as I said, that the concept is defined in the introduction, you can use just find textual answer, Wolfram functionality, to find the special sentence where a specific concept is defined. But of course, the LLMs typically work better. And you can use them also to explain authors, create author reports. And this is conveniently done both by scraping introductions and summarizing them through the new functionality text summarize. So that even with many articles, they are fed into a final LLM function, which with those informations on IDs and titles and abstracts, can create, hopefully, an accurate author report with no fake references. So, some conclusion. I hope you can find interesting using this Paclet, as I found several academic researchers, colleagues found very interesting. And I should say it's also very easy to come up with these high-level functions thanks to the powerful Wolfram language. Of course, many more applications can be developed and further improvements. I hope to find time to develop. But to conclude, some final reflection. So the fact is that this is difficult data to analyze. Typically, only a few people in the world can understand an academic paper, as if each of these 2.5 million points is like a separate universe. And most of the time, thinking at this graph, researchers work in the intersection between blue and green. So they deal with deep, difficult problems, deep data, with the methods of computation, often Wolfram language. More recently, Wolfram implemented the possibility of using LLMs in a computationally accurate way. And but one can think to go further in the future and trying to automate as far as possible the process of research. But this still seems a very difficult problem, because even the capability of expressing abstract concepts is still under development. We saw that with the new functionality array symbol or vector symbol for tensor algebra. Then automating derivations and proofs is an ongoing challenge, which can be solved in simple textbook case, like for the LLM benchmarking project, but it's still very difficult problem in research at the research level. For this reason, I think this is a different kind of very dense and difficult data to analyze, and a long-term goal for Wolfram developers could be to effectively integrate large language models, computational language, and this deep data. With this, I thank you for your attention, and please ask questions if you have. Yeah, okay. I can share a presentation worker notebook. It will be shared, but I'll put it on the chat, the link now. Okay. Okay, thank you for appreciation in the chat. So what was the motivation for developing the Paclet? Yeah, interesting question. Yeah, and I have to say, probably I began working on this because I was scared of ArXiv. I mean, I was working in Nordita, the Nordic Institute for Theoretical Physics. I was just a visitor, even though we are a long-term visitor. They had these meetings on ArXiv every week. They discussed the new papers on ArXiv. So yeah, I could talk and present my papers, but you know, ArXiv was a scary thing because yeah. But I thought that with what I learned with Wolfram, so allowed me to do something better than just looking every day at the new papers and hope that the competitors didn't come up with the same research ideas as mine. So I could try to analyze them globally. And indeed, then I happened to use these plots, these data analysis in my seminars. Yeah, it's interesting for researchers typically, but it's also very easy. And so let's go to the Q&A. Another question. Is this only based on imported text files? Not only. It's a difficult thing to import text. Sometimes there are bugs, more often than not, if you go on a big scale. I hope it will be improved or at least made safe. But as I said, there is the main data set available on Kaggle. You can go in the kernel file and download by yourself every time you want with the program I wrote. Have you found surprising cluster of papers that were not expected? I actually no. I found only what I expected, but I should explore further. And of course, it is possible to find it. I should improve the recommendation algorithm. It was implemented since the last third version. And other question? Okay, thank you for appreciation. Okay, since there are no more questions, so hopefully we can join other sessions, and I will be happy to answer other questions if you have by email.